the safe exploitation of geothermal systems, that is the production of energy exploiting deep reservoirs between 1 and 4 kilometer depth, where the temperature can go up to 400 Celsius and there is water to inject and extract, requires the full knowledge of the seismic cycle in the presence of hot and pressurized fluids. Most of this knowledge usually come from experiments performed in the lab, then also from seismological geophysical studies and the studies of outcrops where the rocks are exposed at the surface, the fault rocks. In this particular case, in this study we published in Nature Communications, we want to understand how fluid-rock interaction occurs when the water can change the physical state. So from vapor conditions to liquid conditions, and if the temperature is larger, higher than 374 Celsius, and the pressure more than 22 megapascal, which is something that can happen at 1 kilometer depth, well, the water goes in supercritical state. To do this, we exploited a new experimental machine which includes, in this particular case, is a rotary shear machine that we have here in Padua University, and a particular hydrothermal vessel that we call Hydros. In this vessel, we can install small samples of rock. The diameter of the cylinders we use is about 3 centimeters, and we can inject fluids with a pressure pump, a syringe pump, that can pressurize the fluids up to 700 atmospheres, while the temperature in the vessel here can go up to 450 Celsius. In this way, we can study fluid-rock interaction and maybe what happens in a real geothermal field where fluids are injected at high pressure. We can study the seismic cycle in these conditions. Now, one of the outcomes of this study, which was overlooked in the past, is that the strength of faults can change a lot when the fluid is, for instance, in supercritical state or liquid state at, let's say, 300, 350 Celsius, and then there is a phase change of water to vapor because of the pressurization, for instance. In fact, our experiments show that the friction doubles of the rock from when the water changes from supercritical or liquid at high temperature to vapor state. What is the geological significance of all this? Is that when you have the fluids coming up from deep, for instance, going upwards, because of the depressurization, there is a physical change of water from supercritical or liquid at high temperature to vapor. And while the fault maybe can creep slowly under liquid or supercritical conditions of water, because friction doubles, basically the creep is locked. So the faults are locked when the water changes into vapor state. At that point, the wall rocks can store elastic strain energy, and thus that will be released by earthquakes. So this is quite surprising. The role of the state of water have been overlooked in the past, and we of course need to do more and more studies to understand why this happens first, why water is allow a different behavior of the fault with respect to supercritical liquid states, and also what kind of fluid rock interactions, that means chemical reactions occur under these stages. We need to study more in collaboration with people with different background. So geochemists and other, of course, colleagues that are working in geothermal fields or volcanic systems. In this particular case, our experiments have been performed mainly in China during COVID and a bit here with our machine. There are only 2 machines of this kind in the world, and the other one is installed in Beijing. So I really thank the Chinese colleagues, but also the Italian civil protection that paid for the installation of this vessel here.